I was not here.
Okay. Now we can hear you.
So give me a second. Let me share my screen.
Hi guys, I think I'm the leader of discussion. So Pedro, if you allowed me, I would like to state 2 questions before the presentations.
Well, I don't know. If you want to do it, it's okay.
But
yeah.
Why you want to do that? I mean,
yeah, it's just 2 questions. Maybe in the presentations, I just want to know. I at the end of the presentation, maybe we can talk about that questions.
Why not?
Because what I want is maybe I want to hear your answers, right? So
but
yeah.
Saul, I think it's better to hear first the presentation, then we have that discussion part. It's not like more like
okay.
question answer. So let him talk so everyone can have a better idea about the topic.
Yeah, actually, I'm not expecting any answer. I just want to leave that questions. So at the end, we can discuss about that. So
okay.
They are just open questions.
Okay, so you want to basically, okay, say them so we can have them in mind.
Okay, that's right. So I think all of us have heard a famous quote in Mexico that it's which comes first, the chicken or the egg, right? So I just want to ask, what do you think, guys? What helped the big data to grow up or to have success? I mean, the big data on itself, or the technology related, or the technology that was available at that moment. If the technology helps the big data, or if the big data makes the technology to evolve. I'm clear with my question.
So that this is the one.
Yeah, that's one.
Okay, so let's hear the presentation so everyone can have basically listen to the presentation having this in mind. So hopefully after this we can all discuss about this.
Yeah.
Thanks all.
That's right.
But stay here, okay? Don't go here. And you can put that question in the Google Sheet. So we can have it also in a written format. The link is in the chat if you don't have it. So let's hear Pedro's talk. Go ahead.
Okay. I will. Can you see my presentation?
Yeah, but in the normal mode, not in presentation.
Yeah. Now I'm going to change it to the. Okay. Can you see enough?
Yep.
Okay. Hi guys. Basically, today we're going to talk about big data. We are going to analyze the workflow of the big data and how the author has found some challenges and how right now they are trying to solve those challenges. Okay. So first, we have some definitions. Well, maybe some of you know those definitions. Maybe some of you they don't know those definitions, especially the third and the fourth one. I want to say what is a batch data and stream data. Well, actually, it's processing or stream processing. Well, because we are going to use a lot of batch processing and stream processing in this presentation. So basically, big data is refers to collecting, analyzing, and processing a lot of information. Okay, voluminous data, basically. And orchestration, orchestration is like like the name saying, it came from orchestra, like when a director or a person that is managing how everything is going. In this case, orchestration for computing is more like configuration, coordination, and management of software or process. Okay, and now for batch data, batch processing. Batch processing is when a task or a job is done without barely without human interaction, basically like a small human interaction. So like some scripting or tasks that you have automated for doing, that's batch processing. And stream processing is like when you have like a continuous flow of data going into your a system or application. Like in the case of when you have a system that can process a video from a camera that is outside your house, for example, that is a stream processing, because it's supposed that each time you are getting data. Okay, so basically that's the four definitions that I wanted to tell you. And then well, introduction. When we are talking about processing big data, we have like three big challenge. The first one is the large data sets. The second one are the types, and store and analyze that data. The large data set, well, like the name said, like big data, we have always like a lot of information when processing big data. Imagine Amazon that is always processing the packages that are being delivered at the time, or Uber trying to analyzing all the offers and that the customers are doing, so they can adjust the pricing. Okay, in the same way, the types of the data. Sometimes when you have like a big data, you will have different kind of data. You will have like video data. You will have sound, music. Well, not music, but sounds data. A lot of data you will need to analyze. So in this case, big data, the challenge is that you have like a heterogeneous data. So you will have like a what is that? Spoiler.
I think I put it down. I'm playing around with Zoom. I just put it that so everyone can see your face when you're talking. I think everyone can see your face, right? When he's talking. Okay. Yeah, that's the one. Sorry.
Okay. Well, and then having a big volume of data means that we need to have like the appropriate store and also the appropriate computing for analyzing those volumes of data, right? So those three are the big challenges that we have when processing big data. And now we have a workflow that we are analyzed right now. So that's a little example of how processing big data works. First time we have here the big data workflow. And then we have the big data programming model frameworks and the cloud edge data center. Basically, when processing big data, we have three layers. Those three are the layers that are used for processing big data. So the first one, that is the workflow, basically is how the process is done from start to the end. In this case, as we can see, first we are going to pre-process the stream. How? We don't know how we're going to do it. The only thing that we know is that we need to pre-process the data that we are going to get. And it can be raw data or it can be from a file. Later we will see it. Then we are going to aggregate some events, like maybe you need to add some metadata to that data for like timestamps or things that are useful for our systems. And then in the cluster events, we are also going to separate the data according to how we want to group that data. So then that data go to extract pattern. So we are going to try to find patterns with that data. So at the end, we are going to find some outliers, and that outliers are going to mean for us something. We don't know what we are going to do, but we know that those outliers are something for us. In this case, this workflow is for detecting anomalies in a system. So the outliers are going to be our anomalies in the system. So then after that, we're going to match those patterns. So give me a second. So we know once we have the pattern, we can do something with those outliers. Maybe we can remove those outliers. Maybe we need to take a look at those outliers. So we're going to match those patterns via custom patterns. So basically, that is like the workflow that we are going to do. But now, in the models, we're going to match those workflow into how we're going to do technically that part. So in this case, the data ingestion, how we are going to ingest the data. Maybe we're going to use like a file that we already have, a data set that we already have, or maybe we're going to like in the batch processing, we're going to process that data via a big file, or we are going to also always processing the data that is coming. But at the same time, this data needs to be analyzed. So maybe in this case, this is more like a hybrid model. In this case, first we're going to analyze the data. We're going to find the patterns. And once we know what we're going to do with the patterns, we are going to apply those patterns to the data that is coming via stream processing. And at the end, we need to save all the process that we do is going to generate some outcome, and that outcome need to be saved. We can use SQL databases, or we can use NoSQL databases like in the NoSQL like MongoDB, like Cassandra. In SQL, like we can use like Oracle or MySQL or SQL Server or something like that. In the case here, for batch processing and stream processing, we have different platforms that can be used for doing that. Like we have Apache Hadoop. We have for Apache Hadoop for batch processing, and Apache Storm for stream processing. Those are the more famous platforms that are used for this. But at the same time, in the cloud data center, we also, for computing everything we need to use cloud for doing that. So for example, for data centers, we're going to use virtual machines. We need to do some storage, or also we need to use the network for moving our data. And if you remember in the past presentations, we used to see some models for getting the with data in the cloud. This is more related to the MEC, the Edge data center. So we are going to have some Edge services and Edge gateways nodes for getting all our data. Okay. Here in this side of the presentation, we can see the challenges that we're going to have for getting this workflow work. In this case, we have these two layers are going to present the workflow related challenges. These two layers are more to workflow data related challenges. And also these two are for the cloud related challenges. So now we're going to analyze the layers one by one. So for the model, for the let me see here. Yeah, for the workflow level, we have managing the sequences of analytic stacks that needs to deal with the static and dynamic data sets in various data sources. This is something that we need to do in the workflow level. This should provide guidance for domain experts. It means that it's whatever we do here is going to be our guide for applying this to the framework level. So for example, if you say, oh, I'm going to get the data here, I'm going to use MapReduce. So if I'm going to do MapReduce, I'm going to match this with Hadoop Apache in the other one, and that kind of stuff. And then we have workflow mapping. That is what I am already doing. That is mapping the analytic task to big data platforms and edge resources and cloud resources. That's for the workflow level. And then for the big data models, in this layer is defined the models that are going to solve each one of the steps that we already have in the workflow layer. In this case, and this is very important because not each step of the workflow model from the workflow layer is going to be matched with each step in the model. One step in the analytical can be done by different models at the same time. It depends on the type of the data that is analyzed. And well, these models are covering everything, like ingesting, storing, and processing all the big data. In the next step, we are going to see the models. We have all these different models that can be used. We have the MapReduce programming model. Well, in the course that we had with Mari, I think everything now, remember that course that we have in the first part of the course that we need to develop a MapReduce project. So basically, this is what MapReduce is done. Like we have two functions, map and reduce, and we have to, in the first part, we are going to generate a key value pair, and then in the reduce part, we're going to reduce those pairs to the minimal expression. For doing that, normally is Apache Hadoop, the platform that can help us to apply that model. For the stream programming model, like I previously said, we're going to have like a continuous flow of data coming into our system. So for that model, we have the Apache Storms. For the SQL models, those models are for storing data. Well, the NoSQL is no. Well, those are the way the NoSQL is not. I don't remember the word for the kind of databases.
Relational, no relational?
No relational, yeah, no relationals. And for SQL, we have the relational databases. Then for the message ingestion model, sometimes we need to use messages for communicating between our steps. So for that one, we are using AWS Kinesis. And sometimes we need to use hybrid models. Hybrid models, it means that sometimes you need to analyze via batch streaming, and sometimes you need to analyze via stream processing. So Google Cloud Dataflow allow us to do the both models at the same time. And then we have Lambda model and Kappa model. I don't remember well how those work. So let me see my notes. Oh yeah, I remember now. The Lambda model basically, even if you have batch and you have streaming processing, Lambda model is going to behave like everything that you get into your system is going to be batch processing. The Kappa model is the other is the opposite to Lambda. Kappa model basically each information that is getting into your system is going to be treated like a stream. It's not going to be even if this is a batch, it's going to do some algorithm that is going to behave like if the data is a stream. For getting that, we have Apache Sparks. Okay. Then, well, this is a table, a comparison between the different big data programming models. In the In the reading, you can find a bigger table with the pros and cons. I didn't put it here because we're going to be a lot of data in just one table. So for that reason, I just put the, for example, the data flow for MapReduce programming model is static. For stream, well, it's streaming. For NoSQL is transactional. If for messaging station, also is streaming. The data volume, when we are working with batch, we know the data because we have a file and we have everything that is there. But when we are working with, when streaming, we never know how much data we have because it is coming every time. Okay. And we have other things here. So if you want to learn more about this, well, in the paper, you can find the full table. Okay, then we have the cloud and edge data center level. Remember, there are 3 layers. We have analyzed 2 of them, the frameworks and the workflow. This is the 3rd one, that is the data center levels. Well, in this case, the complexity is the, well, like in the same way, like we say, we have already studied in another presentations, depending when you are using edge, you will have variety of devices, you're going to have variety of data. So basically, here the challenge is how to manage the heterogeneous information. Then the requirements of big data workflow in the cloud. This is something that we also have already studied. Well, for computing, we need the CPU. We need to have provisioning for for getting all the resources that we want for computing. The same way for storage requirement. Maybe we need the cloud storage. We will need other kinds of storage, but that's the requirements that we need for the big data. Data movement. When you are going to have your analyze your data in the cloud, well, you will need to move that data. Maybe you will need to move the data from your computing to the cloud or from edge devices to the cloud. Also, when you are doing your workflow, you will need to sometimes move your data from one region to another region or something like that. Well, we have a lot of other requirements like synchronization and asynchronization requirements. Analytic task scheduling and execution, service levels agreement, security, very important, and monitoring and failure tolerance requirement. All those requirements are provisioned by the cloud. And then we have some challenges and approaches for cloud. For example, for cloud platform heterogeneity, this is more related to how when you are working with big data, sometimes you have information from different clouds. So it's not easy to sometimes to work with. If you are the administrator of the application that is doing the big data, sometimes when you are working with a cloud, you need to learn how the API works. Sometimes you need to, well, not sometimes, you need to work, you need to learn about pricing, about format, and all those kinds of stuff. So that's the challenge, how we are going to integrate everything so we can work with different platforms without problem. So for that challenges, we have 2 approaches that are already running: the standardization approach and the intermediation approach. The first one basically is like getting a system that can be implemented in just one time, so all clouds can work like without problem, without we don't need to learn a lot of the different clouds because we have the same standard in all the clouds, right? Well, the thing is here is the platforms or the providers doesn't want to do that because that implement a chain architecture or something like that. So for the reason this challenge, this challenge is still working, but it's still not full completed. And the intermediation approach basically is that like having a intermediate layer And that layer is the one that communicates with the API. So you, like a user, just need to communicate with that layer. So in that way, you don't need to learn about the API, because the intermediation layer is doing everything for you. In the same way, for cross-cloud workflow migration, sometimes you have everything in your cloud, but for some reasons, like for example, another cloud is giving you a better price or a better performance, so you want to migrate all your data to the new cloud. That's the challenge. How you are going to migrate your data from one cloud to another cloud? So for that, we have 3 different approaches: workflow abstraction, cloud broker base, and container. This is the one for the abstraction. Basically, is saying that we need to have a better techniques for abstracting the data. It's not a lot of information about that in the paper, or maybe I didn't understand well. For the other ones, like the container-based approach, well, that's something that we already have learned. With container, it's easier to migrate a container from one cloud to another cloud, because all the clouds have like like support for containers. So if you need to move your cloud from one to another, well, you just need to move your container from one cloud to another one, and everything is going to be easier. Okay. Then the resource provisioning, in the same way, like we previously see, when we have the presentation about Elasticsearch, well, this is something like that. Basically, how we are going to provision our computing with resources. Well, we have a static and dynamic. The static one is the one when you previously, before doing starting the workflow, you can set which resources you are going to need. But well, the dynamic one is when the workflow is still running, the resources are addressed or provisioned while doing everything. So the first one, the static one, can have under provision or over provision, and the dynamic one is the one that is the way for trying to avoid under provision or over provision. Then we have resource volatility. Well, the VM one basically is well, the volatility is that, well, the sources in the cloud are not forever for us. They are for us while we can pay for them, or sometimes even if we pay for them, there are some failures that for some reason are going to remove those resources from us. And imagine if you are processing like a big quantity of data, and then you have a failure, well, you will have a big problem there, right? Because you will need to, if you have deadlines, you will need to somehow solve those problems. So for VM level mitigation approach, basically it says that you need to do like a checkpoint in the VM. So you do a checkpoint in the VM periodically. So if you have a failure, you can restore the VM, so you don't need to start from scratch. Then the big data processing framework level mitigation. That one is about improving the frameworks that we already have, right? Like in the MapReduce, like in some way the Hadoop or the other platforms that are doing that process can take like some checkpoints also for saving the state of the process. Also, we have the data related challenges. For the data, we have a lot of challenges. Well, it's big data. It is supposed that should be like that. Well, the data storage, we will have a lot of problems with storing a lot of data. because it's pricing and because sometimes the latency can affect your computing or something like that. So for that, there are two approaches that we have there is the cloud storage. The cloud storage is the storage that is provided by the cloud. And then we have the shared cloud bucket file system. In that thing, we have a file system that is shared in a cloud storage. So it can be being accessed from different nodes, or also you can have like a cloud of clouds that is a file system shared in different in a lot of storage services by different clouds. Also, we have the data movement. Well, like the name says, when you need to move the data, it's a big challenge to move a voluminous data from one point to another point. So we have three approaches there: data transfer, data locality, and collocation of data and computations. In the first one, it doesn't matter where the workers are. So basically, you want to have your data near to your computing. In the second one, it's important where the workers are. So the workers are going to do everything for working with your data in the better approach. Like when the workers doesn't have a task doing, they are going to ask for the data and something like that. Also, we have data provenance. Data provenance, sometimes you need to know where your data comes from or when your data arrives. So for getting that information, you can have coarse-grained provenance or fine-grained provenance. Those data, I don't remember well those challenges, those approaches, but I think some of them are like adding, like adding data, adding metadata to the data that you already have. Then we have data indexing. We have three there: traditional, A-based indexing, and collaborative. The traditional, well, is using models that we already have well, data indexing. First data indexing is done for trying to have faster access into the data, right? So if you want to do that, the problem is that when you are going to do data indexing, you need to have more storage for those index. So we have three ways, like I say: traditional, A-based, and collaborative. The traditional is doing patterns that we already have, or some other structures that we already have, like a tree. I don't remember well, but I think tree was one of them. I don't remember the other, sorry. And the E-based indexing, basically the intelligence, the artificial intelligence is going to try to find some patterns into the data so they can access the data better. And the collaborative is a mixing between the traditional and the A-based indexing. Then we have data security and privacy. The data security and privacy, that's a big topic. Even the author says that when trying to when talking about data security, they prefer to leave this out because it's a big topic. So that's out of the scope of the study for this paper. And then we have the workflow related challenges and approaches. The first one, the workflow specification language, basically is a problem for understanding the workflow, because you will have the workflow, but you sometimes don't know. It's some kind of difficult to understand what the workflow is doing. So what they are trying to do here is trying to generate some kind of language that is more human friendly. so you can implement those the workflow in a better way into the frameworks. Then we have the workflow initialization. That is in both workflow initialization is basically how you prepare your data for being analyzed in parallelization and distributed systems. So the not constrained basically is not taking any constraints beside the task and dependencies or the data that is going to have the data that you are going to do. So you're going to generate your blocks just taking in account dependencies and the tasks that are going to analyze the data. In the constraint one, you also are going to take in account another constraints, like for example, in what are going to be the nodes that are going to be executing the data, or when this data is going to be executed, or something like that. And then after your data has been initialized, you need to analyze how you are going to parallelize and schedule that that data. So we have 3 here. Actually, it's 4. I forgot to put 1 there. But the first 2 basically is for parallelism. The other 2 are for the scheduling. And in the first one, in the parallelism, is how the data is going to be sent to the different workers. In the first one, the data is sent to the first one. Sorry, I forgot how those works. But the push one for the scheduling is a little bit easier. In the push one, just push your when you are going to schedule something, you push your task to the resources that you have available at the moment. That's the push-based scheduling. The one that is missing there is the pull-based scheduling. In that one, the workers are going to, when they are going to be idle, when they are free of tasks, they are going to ask to a scheduler if they can get some task for doing at the moment. So the scheduler is going to try to find the better task that can run in that worker with the resources that they have already there. And then we have the workflow fault tolerance. We have two approaches here. The reactive and the proactive. The reactive is when you already have the failure. The proactive is before you have the failure. In both cases, they work in 2 different ways, with workflow or with task. In the reactive one, they are going to, if the workflow fail, see something in the workflow fails, they are going to try to solve the problem. The same way for the task, if a task fails, they're going to try to solve the problem. In the proactive, if they detect that the workflow is going to fail because they have seen some error, they are going to remove that part of the workflow, and they are going to replace that component with the component from another workflow that is working. The same way the task, if they detect that a task is going to fail, they are going to remove that task with and replace with another task that is working as expected. In the same way for the workflow, they are trying to leave out the security for the workflow because that's a topic that is for beyond the scope of the paper. And at the end, we have some open issues. Some problems that they still doesn't have solved, like the workflow interoperability and openness, the workflow fault tolerance and dependability, distributed workflow execution, workflow security, like I previously said, user perspective, cross-cloud workflow migration management. It's still not fully solved. Workflow resources operability and volatility, also not totally solved, and cross-layer resources configuration selection. And that's all my presentation. I don't know if you have some questions.
Thank you, Pedro, for the presentation. It was I think one of the longest paper so far with a lot of content. But thanks for the presentation. So let's hear from the discussion.
Yeah.
Yes.
There are any question?
Well, so what's first, technology or big data?
Okay, if you have any questions related to the presentation, I can solve it. Well, I can try to answer the question, or if you already want to go to the main question from Saul, is also good.
Well, I have a question for all the group. We're talking about big data, but where do you think the big data engage with artificial intelligence, deep learning, and well, yeah, with artificial intelligence and deep learning, because that's also a huge amount of data. Since my point of view, the big data covers artificial intelligence, deep learning, machine learning. I guess everything is inside the big data. I don't know if you see the same, or do you have a different opinion?
Well, I think the big data is more like the ingestion of those data into the artificial intelligence. It's more like the source of data that is going to be part of the intelligence.
The source.
Yes, I think that big data is in charge of, of collecting all the data and processing it. But artificial intelligence is the one that actually uses it to, to create knowledge or do things.
Yeah, I mean, I do also think in that sense, in that big data is like an enabler of artificial intelligence. I mean, many times we have said, or there was like theories in the past that, okay, if we could gather enough information to make these decisions, then this would be right. I mean, right now we do have access to all that information. So basically it is what has made most of the artificial intelligence and machine learning advances possible.
So big data enables artificial intelligence and everything else. So big data is the platform, and over it's the remaining models: artificial intelligence, deep learning, machine learning.
Yeah, I mean, it just like hangs in there. It just depends on it like a lot, right?
Right. Thank you.
Will it be
Yeah.
more like the artificial intelligence will be the processor and big data the information, something like that? Yes. Right. They complement each other.
We also see the difference with Dr. Falcon, in which there are many labels. For example, the big data, it's the gathering of all the data, but it's only information, and we need to process it to get some insights in the information, and then what is the name of the role? I don't know, but it's the to transform that data to some model useful for the company, and then transform it to machine learning models to predict or to classify some information for the company itself. So
Okay,
there are many layers.
I'm going to share again, and I want to here. Let me. Okay. as we can see here in the workflow, big data, processing big data is everything here. From getting the information, processing some kind of information, and in artificial intelligence would be here in this part, where you are going to get patterns, you are going to match those patterns, and you are going to do something, whatever you have there. So yeah, in some way, artificial intelligence, it's linked with big data, but it's not like they can work in a different ways, and they can be isolated one from another, but also they can be complemented.
Yeah, I mean, big data is more like about the pipeline, right? Like about ingesting a ton of stuff and then moving it from one place to another and transforming that data into information. And once it's in a more distilled format, you can pass it to a machine learning model, right? But like the machine learning model would probably not take as input like all the stuff coming into your big data pipeline, right? So I think about it more as a pipeline kind of problem solving.
Yeah, I think another way to see big data is like a raw material, materia prima. Big data is in charge to collect, process a big amount of data, and artificial intelligence is just, let's say, I forgot the word. Fábrica?
Factory?
Factory, yeah. It's like a factory that uses big data, but big data is not its main raw material. For example, there are artificial intelligence who use images or use cameras. So they are not use only data or information. They can use another kind of input, right? So big data just analyze the data and can be used by any other processes. But I think the confusion comes from that one of the main inputs from the artificial intelligence is, of course, the big data, right? For example, finance, business, social media, they need to process a lot of information to try to predict or to try to provide some future expectations for a certain kind of business or work. But yeah, I think big data is more related like a raw material. Any other questions? Something that you want to point out?
I have one last quick question.
Yep.
So, for example, with this paper and the recent ones that we have seen in class, do you think that for the big data usability, it will be only restricted for huge business, or it will be worth it for personal projects, small companies? Because we've seen that it requires some amount of payment depending on the use and the implementation. It's not easy. And also Pedro mentioned about the languages to work with big data are not like the most user-friendly.
Well, actually, it's not like it depends on the quantity of data, right? It can work for small companies because one of the advantages of having the cloud is that you can have resources that you need without spending with a lot of money on them. That's one of the advantages of the cloud. So yeah, maybe you will need to pay a little bit for doing your stuff, and you don't have all the economic resources that a big company is going to have. But you can do some big data. I think the main problem here is how to get the data more than processing the data. If you are a small company, maybe you don't have like that amount of data that you need for getting your patterns. But in difference with a big company that they have all the resources for doing that.
Yeah, that, and also what about like security and privacy? I mean, maybe I can just go on and set like a housing business and gather information from everyone, but when does it state that information I can use it for whatever that I want, right? I mean, maybe it's some place that I rented to someone and I'm gathering information from that place. And I could say, hey, it's my place, so whatever I gather here is mine, but not necessarily, right? I mean, when did they give me the permissions to actually start gathering data about them? So I guess that's one of the very big challenges, right? I mean, and we have seen it, for example, I think it happened once we had like tons of challenges or like competitions in images that were using Pinterest images. And then Pinterest just said, hey, those are my images, just stop using them. And then basically most of the competition that are related to image processing was just like delayed for 1 year or so until we had like enough information to continue doing the competitions again. I mean, because again, they started the competition saying this information is from everyone, and Pinterest was like, no, I mean, people paid for having that information and is not to be used in that way.
Well, related with the company side comment, I would like to add that at the end, when you create a big data or data solution, you want to create something that you want to create something that can scale. You want to create a modular solution. So at the end, your data and your solution can grow together. And also related with the Ricardo comment. At the end, I feel like a lot of time people think that big data and machine learning are something different. For example, that you are going to use the big data techniques or solutions in order to transform, obtain, and store your data, and then you are going to use something different in order to create the machine learning models. But that, I feel like it's the same, because I mean, if you are working in a real big data problem, you are going to need a machine learning for big data solution. So, for example, as Pedro told us, when you are working with big data, one of the principal solutions is Spark, where you can work with the ingestion, transformation, analytics, and also you can create the models, because it's really hard to work with a lot of millions of records, and then that you try to you want to create models with a normal technique or something like that. So I feel like you are going to work in different layers, but at the end with the same approach that it's big data. So that's it.
I have a quick question. What could be the limit or the threshold to call something is big data? It's the amount of data, or it's the amount of time to process those data? I don't know if there is a mark limit.
Well, big data, like I said at the start of the presentation, it's gathering, processing, and storing big volumes of data.
But we don't. Yeah, but I mean, the question is how big? Like, is 1 terabyte per second big data, or is 1 petabyte per second big data? Like, I mean, I guess the definition is
for modern standards is always improving the limit amount of data that we can process in a machine. But
yeah,
I don't know.
Yeah, but again, you are going like I said in the presentation, there are 2 approaches for doing this: batch processing or stream processing. In batch processing, you have like a amount of data, a definite a known amount of data. But stream processing, you never know the quantity of data that you're going to process, and it's still called big data. You're going to analyze everything that is going into your system at the time, but you don't know the quantity of data.
Well, I guess it depends a lot also on, I mean,
Yeah.
like we're looking a lot like at the threshold. I mean, and it does depend a lot on what we are measuring, right? I mean, if we are measuring like the things that we can get different, like actual information that is different every second, then, for example, gathering information from 1 year is a lot. But I don't know, if we're measuring how many mass extinctions have been on the Earth's history, probably 3 significant measurements are a lot, right? So yeah, I mean, there's no like real threshold in that. It's just enough data so that you know that you have like at least represented in a real way whatever you're trying to measure.
Yeah, true. As Rodrigo said, I didn't know even really. I just Googled and there's something came up. So the one that I posted and what Rodrigo said is perfectly makes sense. Depend on the era we are living in, the concept can totally change. And maybe also depend on who you are talking with and the processing power that you're having under your control, the concept can change. Maybe one, like, I don't know, 100 terabyte is really, really big data for me, but for massive or giant companies, nothing, right?
Yeah, I mean, considering the request per second that Facebook or Google gets, like maybe like 1 terabyte of data per second to most companies in the world is like, oh my God, this is way too much. But for those, it's like, it's like pocket change of data, right? So I guess it also depends on your computing power and what. I mean, I guess it depends on a lot of things. I find it a very like buzzwordy catch-all term, and I don't quite like it. But yeah, it's just a lot of data.
Yeah, just a lot of data. Yeah, so it can depend, but it's a nice question. I mean, I never thought about it really, like how big it should be to call it big data. But yeah, I mean, whatever you're saying, it totally makes sense. I mean, it depends.
Great, thanks.
Any other questions?
I just have one question for something that I would like to discuss. In my opinion, please correct me, it seems like the storage and memory is the resource that it's scaling more in a linear way than, for example, CPU or the networks, that kind of stuff. So probably because that is the fastest one. Actually, I was taking a look into the prices and the amount of data that we're able to process. I mean, right now, a hard disk is pretty damn cheap. I mean, it's something that everyone can have, but for really, I mean, looks like the way that the storage, the data, it's not the problem now. Now it's how we can process it, because the computer processing, it's not scaling in the same way. I'm not sure if, I mean, my comment here makes sense.
Well, I think everything counts, not just one thing. Like, for example, when you need to storage data, well, when you have big quantity of data, it's a problem because of the price, and it's a problem because of the resources. And also sometimes you need to avoid, for some processes, you need to avoid latency. So also it is important where you are storing your data, because maybe you want to have your data in a region near where you have your computing doing. So at the end, I think everything counts.
But isn't it a network issue?
Sorry?
Isn't it a network issue for that specific case? It's a limitation on the network or the computer processing more than in the storage itself.
Well, I think it depends on the process that you are doing, the processing that you are doing.
Okay.
Yeah, your question remember me my morning's work, because in the morning we received a message saying that our system were unable to produce more documents. That it's what we are doing, and that's because we run out of space. So our servers run out of space, and I think one of the most important things that it's more valuable is it's the storage. Of course, depends on the kind of or the type of applications, but I think the storage it's one of the resources that needs to be increased consistently or in the time. a lot of resources or a lot of applications. Currently, with the computer processing that we have right now, I think almost every computer or almost all computers can do every task. So it needs to be a really hard work, a really hard task to request a lot of computer resourcing. But yeah, I think the storage it's the most valuable resource.
So, but Oscar, I didn't quite get the question. Like, you're asking which part of the pipeline like lies the bigger costs, or?
No, what I am saying here, yeah, sort of. Looks like all this progress that we are getting in artificial intelligence, big data, all this data processing, it's just because if you check the amount of data that we were able to store 20 years ago, you had to take care a lot of how you are going to store it to keep it as minimal as possible. And that was because we have a memory limitation. Today, that limitation doesn't exist. You can buy 8 terabytes of a hard drive of 8 terabytes for almost 3,000 pesos. I mean, just to say, give an example. But in the case of the CPU, the GPU, and all the other resources, the network resources, they are not scaling in the same way. That is like the challenge.
The bottleneck.
Yeah, I mean, the bottleneck, it's not in the data now, it's in all the other.
Yeah, I mean, I guess it depends on your application, right? Like if you can like receive huge amounts of data and store them like for days and analyze them asynchronously, then you don't really care if you're in a like shitty hard drive that it takes forever to take the data off because like you don't care. But if your application is like kind of real time-ish, then maybe you need to throw a lot of money at the problem and have like in-memory databases so that queries happen like sub-microsecond latency, that kind of stuff. So I mean, yeah, I agree that storage is probably the cheapest part, but depends on the asynchronicity of the task, right?
It doesn't covers all the problems, right?
Yeah. I mean, if I need to, like, I'm getting a lot of data and I need to analyze it like in the next 3 minutes, then probably a hard drive won't do it, right? Like probably in 3 minutes I won't be able to even write it to disk. Let's not talk about like reading it back and like moving it around, right? Like you'll probably need like Redis or some in-memory stuff where like write and read latencies are like super low. But then that makes your storage like really hard, really expensive, right? Like you're talking about like you're throwing memory at the problem, not storage, and memory is expensive. Yeah, but I mean for async, like things that are naturally asynchronous, like maybe like you can train your machine learning model like maybe once a day. So like you just gather a shit ton of data and then just like at midnight you start processing it, right? Like you can just keep it on disk, right? Like you don't need it like to be fast. So I guess it depends on the application.
That is a good point. Thank you.
Yeah, and
also,
I can.
Go ahead, Paul.
Yeah, I have a good example about this topic because maybe in the usual way of computing, the processor and the memory matters more than, or it seems that matters more than storage devices. But that's not entirely true because there are, for example, we at Intel, we have custom CPUs, for example, one for Facebook. And while other customers need more like processing power or processing like more gigahertz or more cores, Facebook is focused only on to have the simplest CPU that they need. They don't need, because like they feature a lot of functions, and only let's say that we only remain the basics only for them to function a big server. They are more focused in storage than speed or cores. It's the other way there. The CPU is cheap and maybe the storage is expensive.
Yeah, not to dive super deep into that, but I don't know if that's entirely true. Yeah, Facebook stores a lot of information, But the graph nature of the queries that Facebook runs is pretty complex. Like running a lot of that directly from disk won't work. So Facebook has a lot of processes running that have like the graph version of the data that's stored on disk. So it's like a very optimized cache for the storage. So yeah, there's a lot of processing going on there.
Yeah, but they do have a lot of applications, different applications. I mean, they do have one CPU specific for them that it has less than 1 gigahertz speed, while others are 3, 2, 4 gigahertz. They don't care about speed in that specific CPU model. Of course, they do have a wide open models for the CPUs that they use in their data centers.
Yeah,
But more like in a NAS, right?
Huh?
That case. For that case, it's more like in a NAS, right? It is just taking care of handling all that data. It doesn't matter if the CPU is not that strong. Sorry, continue, Ricardo.
Yeah, no. I was just gonna say, like, all they care about is the snappy query. So as long as this cache is warm, yeah, you're right. Like they don't need a whole lot of like very powerful processors. Like they have GraphQL and things to make those queries like snappy. But yeah, they definitely, like, pretty much no one that needs real-time latency will pull stuff from disk. Like no one ever in the life. Like you need Memcache and Redis and like in-memory caches all the time. And those cost money, way more than the storage.
Yeah, also, well, this was canceled, but there's a Optane technology that allows you to have big amount of storage in the memory. I don't know if you know that technology. Optane, let's say,
like non-volatile memory.
Yeah, correct. It's the same, non-volatile memory.
Yeah, I don't know much about it.
Yeah, it merges the storage and memory speeds, but it was just canceled recently, so
Okay. I want to stop it like this here because it's quite interesting to talk. The time is short. So thank you so much, Pedro, and everyone that participated in the discussion. It was quite interesting, actually. Quite a lot of interesting specific topics that came up. So if you agree, we can have like 4 minutes break. So we come back 7:50 and we continue because I'm worried that we don't get to finish everything.
Okay.
So we come back 7:50 sharp. So I'm recording.
Can you see the presentation?
Yeah.
Okay. So this presentation is going to be about task scheduling techniques in cloud computing. Before starting, I want to mention that I had to do a lot of research also outside the paper, because the paper mainly describes different implementations of different types of scheduling algorithms. But I think that it makes more sense to review like the key concepts instead of diving into specific implementations. And especially because all this information about the scheduling is new for me. So yeah, probably you're going to see a lot of things that are not in the paper. Okay, let me start. Cloud computing is growing massively. As a result of that, the number of servers and virtual machines is increasing day by day. As we all know, cloud computing is the on-demand availability of computing resources as services over the internet. So it consists basically in a collection of interconnected computers. And the main idea behind it is that users make requests to the cloud. The cloud system processes the request and send back the result to the user. We can see each request submitted to the cloud as tasks. So all the processing that occurs in the cloud is controlled by a critical component known as task scheduling. So cloud task scheduling is a key component in cloud computing. It's the process of arranging the tasks in a particular order for faster performance in the system. The task scheduling process passes through 3 levels, as we can see in this image. The first level is a set of tasks. We can see this also as, I mean, this may come from Codelets. All these tasks are sent by the cloud users here in the first level. In the second level is a scheduling level. It is responsible for making tasks, for mapping tasks to suitable resources to get the highest resource utilization with minimum makespan. And in the third level, we have the virtual machines that are used to execute the tasks from the users. Sorry. Okay, so why task scheduling? Task scheduling is needed because the processing of every task may utilize a lot of virtualized components. So definitely manual scheduling is not an option. Also, the tasks from the users arrive at a different rate of speed, and a massive number of tasks into the cloud without a proper alignment will cause like congestion and slow the whole process. Therefore, cloud scheduling plays a vital role in cloud computing. And the main objective of task scheduling is to efficiently schedule tasks to minimize time loss and maximize the performance in the cloud system. These are some benefits of task scheduling. We have shorter execution time, scalability, improve power utilization, optimal resource usage, faster response time, cost minimization, and also it helps to improve load balance. Then we have the major problems that manifest in task scheduling, which are load balancing. All these are like the challenges: load balancing, scalability, reliability, performance, and finally dynamic relocation of resources to the computing nodes in the VMs. Well, then we have the algorithm. It's the most important part of the cloud scheduling component. It's in charge of scheduling all the tasks appropriately. So the algorithm is selected depending on what needs to be enhanced in the cloud component system. So these are some of the metrics on which the cloud scheduling algorithm can focus. We have makespan, that is the total time taken by the resources to complete the execution of all tasks. Then we have cloud utilization, that is the percentage of time on which the cloud system is busy executing tasks. Then we have tasks priority, energy, delay, and bandwidth. Then we're going to see the classification of these scheduling algorithms. They can be classified according to the mechanism used into these categories. First, we have static scheduling. These ones are considered very simple compared to the dynamic ones. It is based on prior information of the global state of the system, and they don't take into account the current system of the virtual machines. Just so that they like divide all the tasks without taking into account how busy are the machines currently. Then we have dynamic scheduling. Dynamic scheduling distributed tasks according to the current capacity of all the available virtual machines. It doesn't require prior information of the global state of the system. And that's because it takes into account the current state of all the machines. Then we have batch scheduling. In this category, the tasks are grouped into a batch before being sent. It's also called mapping events. Then we have preemptive scheduling. In this one, each task is interrupted during execution and can be moved to another resource to complete it. Then we have non-preemptive scheduling. Here, the virtual machines are not relocated to new tasks until they finish the execution of the current task. And now we are going to see some algorithms that are used for cloud scheduling. First, we have the quality of service parameter-based task scheduling algorithm. In this one, the scheduling is done in view of various criteria known as the quality of service parameters, like the metrics I showed before. This algorithm focuses on the quality of services parameters defined, so it's oriented to satisfy the needs of the system. And yes, it basically works prioritizing certain quality of services over others by assigning weights to them to give more importance to one or other. Then we have the ant colony optimization algorithms based scheduling. This is an example of dynamic task scheduling calculation. It's an arbitrary search algorithm. It mimics the behavior of ant colonies in nature to scan for food and to interface with each other. So the idea is that first all the ants move randomly, and when an ant finds a source of food, it goes back to the colony, leaving markers or pheromones that show the path to the food to the ants. So these yellow things will be the markers. So when other ants come across the marker, they will most likely follow the path. It has certain probability, but most likely they will follow the pheromones left by the other ants. And if they do, then they populate the path with their own markers as they bring back the food to the colony. So as more ants find the path, it gets stronger until there are couple streams of ants traveling to various food sources near the colony. Because the ants drop pheromones every time they bring food, shorter paths are more likely to be stronger, and hence optimizing the solution. And in the meantime, some ants are still randomly like scouting for closer food sources. Then we have the particle swarm optimization, PSO based task scheduling. It has become popular due to its effortlessness and its adequacy in an expansive scope of utilization. It is a meta-heuristic optimization algorithm that works based on the behavior of the birds. So the main idea of this algorithm is the movement towards a promising area to get the global optimum. So the behavior is that each bird or particle adjusts its traveling velocity dynamically according to the flying experiences it has, and also according to the experiences of the other birds in the group. So each bird tries to keep track of their bird, the best result for him, known as personal best, and also the best value, the best global value, of all the birds in the group. And each bird modifies its position according to its current, taking into account its current position, its current speed, and the distance between its current position and his best score, and also the best score of the group. So yeah, the idea is like to use the movement to get and all the information of the group to get to an optimal solution. And then we have genetic algorithm-based task scheduling. We see this one in our class. It's an adaptive heuristic algorithm that is based on the ideas of natural selection and genetics. It's commonly used to generate high-quality solutions for optimization and search problem. And the steps of the algorithm are, well, first we initialize our population and we determine the fitness of our population. And then until all the information converge, we repeat these steps that are select parents from population. Then we cross over and generate a new population and do the mutation on our population. And we calculate the fitness of our new population, and if it meets the criteria, it's done. And if not, we repeat, we select parents again and cross over and mutation and all this again until we meet the desired criteria. And then we have the fuzzy-based scheduling. The term fuzzy refers to things that are not clear. So in the fuzzy system, there is no like absolute truth. There's not only true or false, there's like an intermediate value. present there. So things can be like partially true or partially false. These methods offers an improved ability to identify two elements like text or entities, or I don't know, strings that are similar but not precisely the same. It's to identify like similar things, let's say. Thank you. That's it for my presentation.
Okay, thank you, Juan Carlos.
I am the lead, the
Yeah,
leader.
go ahead.
Someone has a question? No one?
Yeah, I mean, I have actually. So basically, Juan, you mentioned about a lot of algorithms, but you didn't talk, I don't know, the paper didn't talk about which one is suitable in which scenario, but it was more like introducing them, not like saying, okay, in which type of scenario, which one would be useful or better performing comparing to others.
Yeah, I prefer to use the time to define all the concepts, because the paper, like it was like directly describing the implementation, but without describing for example, the algorithms or all those things.
Okay. So yeah, that's it. I mean, if anyone has anything to say, discussion, right, David?
From my side, I prepare some question. For example, task scheduling can be treated as a NP-hard problem, so there is no easy solution to achieve. What new algorithms or technologies could help to improve the performance of task scheduling? For example, I will say quantum computing, because this technology promises to address this kind of optimization problems in the future, for example.
Yeah. Well, I don't know if anyone has any opinion about this. Anyone ever worked with any of these algorithms? Ant colony swarm optimization.
Yeah,
for what?
For any other reason.
The genetic one.
Genetic algorithm.
Yeah.
For
using
may I know for what?
We use that for in the past course that we had.
In a course.
Yeah.
Yeah, we had this evolutionary computing class, and we went through PSO, and as Pedro was saying, genetic algorithm. I mean, like, yeah, the genetic algorithms and other evolutionary computing algorithms, but never for
scheduling.
Yeah, for scheduling. I mean, it does make.
But anyway, the algorithm is not just for scheduling. They are like optimization algorithms, so you can use them for any problem that you're trying to optimize.
Yeah, I guess the most difficult part is not really getting into an algorithm that really does the trick, is actually creating the best representation of the problem itself, right?
Yeah, the abstraction of the problem.
Yeah, I mean, in these cases in which, well, at least from the metrics that we were talking about, like make span and priority and cloud utilization, priority, energy, bandwidth, I mean, it seems like tons of variables. I mean, I guess that probably like visibility of the data at that dimensionality is very difficult. I mean, I do remember that last semester, and when we were presenting the project for that one, I believe it was Manuel. He came up with a problem that was like impossible to represent like graphically. So he had to create like a custom UI for that, and then explain how that worked. And then he just demonstrated that it was working as expected. But yeah, I mean, I think that's I mean, it's not about like, you can get any optimization algorithm, but really the abstraction is like key part.
Yeah, the important, what I didn't, well, what I didn't know is that just for the scheduling, you needed a lot of algorithm. I was thinking that just one algorithm was solving all the full problem, but I see that there are a lot of them, and each one is so different from the other one. But yeah, like, well, from the part that I saw in the big data one, there are different approaches, and everything is related to resources, right? So I think in my case, I just saw the basic one, that is the push and the pull. The push, I need to schedule this task. Use whatever you have. In the pull is, I have this resource that is not doing nothing, and he wants to do something. Well, send the task that he can do at the time. Yeah, but I think those are the simple one, because I saw like the genetic one is not that easy, like Rodrigo said about the extraction. And I was so interested in the ones that are related to animals, the ant ones and the bird ones, how they can replicate those algorithms.
Yes, this is also my second question. So there is a great influence of nature in the mentioned algorithms. So do you know any other example of how nature shows group synchronization? I don't know, for example, they talk about birds and ants, but any other colonies in animal kingdom, or even fungi or plants, also show those behavior to synchronize and improve the optimal way to get food, for example.
Well, there is this algorithm. I'm not super familiar with it, but I know it exists. It's not really based on animals, but rather on physics and on metallurgy. It's called simulated annealing. It has to do with metal, like blacksmithing, like melting and hardening metal. And it reaches like by heating the metal and letting it cool down and heating it again, it reaches some like physical properties, and some crazy people created an algorithm based on that. And I was curious about it, and I found a couple of papers of people looking into using simulated annealing for task scheduling precisely. Like this one, I didn't actually read the whole thing, but I mean, at least people are looking into that. So yeah, that's another one.
Yeah, like fish forage, honey, the bee honey search. We have a lot of these algorithms on evolutive computing. So, and also if you search only for PSO, you will have multiple variants only for PSO, like PSO binary and PSO with so many, plenty applications of PSO. So yeah.
Yeah, because it's quite hot topic, and I don't think it's ever get cold actually, because when you're talking about optimization, it's like it's going to be forever existing problem. I mean, you want to always optimize further and further and further. So the optimization algorithms, I mean, people are always looking for new solutions, either inspired by natures or from what Ricardo was saying. So yeah, there are a lot actually.
Yeah, and I think a big deal why we're using like this type of algorithms is that they are quick, right? I mean, we don't need like a full run to an artificial, like through a deep thing of artificial or of like a neural network or something like that. I mean, this one tends to get to the result quicker than any other that are artificial intelligence related, like really deep learning stuff. I mean, those are kind of slower, and in optimization, we tend to see these kind of algorithms. I mean, sometimes you even see them in like real-time systems, like PID controllers that need like very quick responses. So yeah, I mean, that's why we see tons of that ones here, and we don't see like, I mean, you don't see an example about using a neural network, right? I mean,
yeah, but I mean, I guess the way I see it is more than the speed of the problem is the fact that you have no idea how a good optimization looks like. But in the sense that it's an NP problem, if you see a good solution, you can know if it's a good solution. So it's like algorithm, you do your magic, right? Like you don't have to do anything. Like you just initialize a bunch of random stuff and then just like let them do their thing. So I read somewhere, I don't remember if it was in the paper or elsewhere, that actually the problem with some of these is that they actually take somewhat long to converge. Like if the search space is big, they're actually not that fast. Like they do find like some optimal, no guarantees that it's a global optimal or anything. So that's a drawback of these algorithms always. But yeah, it was part of what I saw in, I believe, one of the simulated annealing is that it tends to be slightly faster than some of the other like PSO. Some other papers also mentioned gradient descent, which is typically like thought of as a machine learning thing. I didn't know it was used elsewhere. But yeah, like these are guided algorithms, right? Like gradient descent has the gradient to point to the maximum or minimum, whatever you want to think about it. But yeah, I mean, the way I think about it is I have no idea like how to even start to solve this problem. Give me a solution and I will tell you if I think it's good, right? So I think that's why these meta heuristic algorithms are used, right? Because of the NP hard nature of the problem.
Actually, we saw that on the class of evolutive computing. I was in the team of Rodrigo, and we saw in a graphic that is called rastrogen. You can search on Google for it. It has multiple local minimums, and we used the PSO because we didn't know what was the global, and the graphic doesn't have a global minimum. So the approach of PSO was really good. And
yeah, and I mean, if you have like a 2 variable function, you might like you are lucky enough to be able to graph it and maybe like you can try to figure out something. But if you have 100 variables, like how do you even start like cramming that into your head and think about it, right? Like the search space is just so big. It's like I'll just let you algorithm do your magic, right? So I mean, there's not a whole lot of guided thing that you can do there. You just need this random search.
Yeah, exactly. I mean, in this case, the task is really complicated things. I mean, scheduling cloud computing, if you imagine how massive it can be, how many different variables can play a role. So it's really like that, what you're saying, Ricardo, like a function of 100 different variables. It's really hard. I mean, that's why we have all these things, all these different approaches for scheduling in cloud computing.
Yeah, it would be really great to really go into a paper, because I mean, we remember that from class, we did like tons of tuning. I mean, many of the algorithms, they had tons of parameters and we had to put in constraints and limits. I mean, it was not like as easy as just let go and that's it. I mean, we had to do like tons of tuning to really get into something working. So yeah, I mean, there, as it says, right, you should have some heuristic into saying just, I mean, you can have like 100 cores, right? I mean, just limited to between 1 and 4 and stuff like that. You do have to add some constraints. And yeah, it would be nice to see in one of these papers that really goes into any of these optimizations is how they tune these parameters. I mean, that's like the most important part, I guess, how they decided which parameter goes into like, okay, do take risks and look for global minima, or don't take risk and take like the first global minimum and stuff like that. I mean, I guess that's what really gives value into these various implementations.
I think what I remember from the last class is the most important part of this algorithm were the heuristic, which is the value that you are going to evaluate, and how this you're going to take the value. More than the abstraction, that is also important. In those kind of things, everything imports, right? But in this case, they say the heuristic was the more important, because if you don't have a good heuristic, you're never going to get nothing. Or you're going to get something that you don't really want to get.
Yeah, but to get good heuristics, you need to understand the problem, right?
Yeah.
And that's how you get, like what Rodrigo was saying, like the interesting things, the constraints of that, well, of those models. So yeah, I think it's really important to understand the problem so you can use your models in a good way and not just throw them into the problem to see if it gives you an answer, right?
Yep.
Yeah, but I mean, as with, oh, sorry.
Go ahead.
With all these things, like it's usually like an iterative process, right? Like you start like you can see it all the time in machine learning, which it kind of gives me the allergy to think about machine learning. Like you just try something and it doesn't work, and you're like, okay, let me move this number, like let me tweak it a bit and let me turn this knob and this other knob, and eventually things make sense. So some things are guided, but I mean, I don't think there's a good way to like just from the get-go like say, oh, these are the optimal parameters. Like it's always an iterative process, right?
That's right. But at the beginning, you can maybe have some idea, right?
Yeah. I mean, if you get like
just random.
If you start thinking about assigning a negative number of virtual machines to your problem, like that's probably not where they're part of the space where you want to be looking into.
That's right.
Yeah, and it's more like really guiding this trade-off. Like we talked about a lot about this trade of exploration versus exploitation. I mean, maybe these problems are more like into exploiting end, right? I mean, they are more into whenever you have, I mean, we know that the global minimum is always close to where you are, so just exploit a lot. Or maybe not, or maybe in these problems, I found out that it is a better solution to explore. So if you have, you find like a good local minima, don't take it as granted, do take some chances and look somewhere else, right? I mean, I don't know for sure. I mean, we would need to go like into these papers and say people have demonstrated that it's better to exploit or that it's better to explore, or I mean, that would be like the better way to understand like the generalization of the problem.
True. Okay. Thank you for everyone. So we can move to the next if you're agree. I don't know, you want to have a break or you want to continue?
Let's go.
Yeah,
Here to
continue. Okay, so let's go with the next one.
I'm going to share my screen.
Yeah, you can go ahead. So he's going to talk about load balancing now. There are tons of problems, really. I mean, I tried to put these three papers next together, but you see most of them are discussing a lot of basically open issues and a lot of problems. So it's interesting, I mean, how we take everything for granted. I mean, when you're using, right? Like, use it, right? I mean, why we should deal with all this, I mean, things even we don't notice as an end user.
I was just searching for what AWS uses to schedule tasks. I didn't find it. So probably they haven't solved it. Probably they have someone scheduling tasks.
Manually passing this.
Okay, so I will start with the presentation. Well, the topic was the issues and challenges of load balancing techniques in cloud computing. This was a survey that two guys made for get like the direct definition of load balancing and and getting a survey about multiple sources of editorials, conferences, and all that stuff to get like some definitions about load balancing, dynamic load balancing, classification, metrics, policy, and all that stuff. So we're going to start. Okay, this is the topics that I'm going to explain a little bit. What is load balancing, the need of load balancing in industry and in the paper, the challenges of load balancing in the cloud, the model classification, metrics and policies that I explained, and the research trends, and a conclusion. So before starting the presentation, this was the sources that the paper has. We get different sources, they mostly from IEEE. So, okay. So what is load balancing? Load balancing, as far as well, in my opinion, is the way how we divide the tasks in multiple systems, VMs, to try to balance the system in terms of workloads. So there's a big need in the industry about load balancing. I would say I work at Intel, so in the infrastructure part of a cluster, so I know the need about the load balancing is really, this is a helpful technique to improve the clouds, the cloud providers to schedule the user tasks on their own platform as a service, I will say, or infrastructure. Because not all time we have the possibility to, as Mari said on the presentation, imagine you one system use it 1,000 hours is the same as 1,000 systems use it 1 hour. So we need to reduce a lot of energy. We need to reduce carbon consumption. We need to make workloads efficient, the tasks, to avoid bottlenecks, and a lot of stuff right there. So then we have right here the challenges of load balancing. There are 7. The first one is the geographical distributed nodes. Imagine that you have 20 systems in 100 racks in a data center, and you want to connect the rack 1, system 1 to the system, I don't know, 20 on the rack 20, send a task, or even the load balancer wants to divide these workloads into these 2 systems, where we will have a lot of network delay. We will have problems with communication, problems with latency, and the distance will be so long. So yeah, in terms of cluster, in my experience, this is true, because imagine that you have a cluster in, I don't know, in US, and you have your master node that is going to divide, well, the master node in this case as a dynamic load balancer in a centralized, in a non-distributed way by centralizing. Or that means that you have one node, one master node with multiple nodes. But imagine you have this master node on the US, and you want to communicate, you want to send the same task to one node that is located also in the US and one node that is located in Shanghai. So do you expect that the network delay is going to be the same? No, that's not true. We saw that it takes time, it's difficult, and well, this is one of the challenges. The second one is the single point of failure. When, well, as I said, imagine that you have a master node, multiple workers in a data center, but if your master node crashes, what happens? with the rest of the workers. Well, the rest of the workers we will not continue with the task that they were executing. Maybe the current task, yes, but not the task that is going to be after that, because they lost the connection. I have an experience right here because someone of my team crashed the master node. We stayed without cluster multiple days. So yes, it's a challenge right here. I will say that distributed system algorithms are a big approach. I don't know if it's only an hypothesis or maybe it's related, because imagine that you have a master node and you are using Raft algorithms or Paxos algorithms and your master node crashes, then you will have an election between the nodes to another being the candidate to be the master node. So there are so many approaches, there are so many reflections that can be right here. The other one is the virtual machine migration. Well, when virtual machines get overloaded, we transfer to a different virtual machine to try to get the load balancing approach. Like this is the approach of, let me check, the sender initiated. When you have a overloaded system and you send to a different underloaded virtual machine. Then we have the heterogeneous nodes. Basically requires executing them, heterogeneous nodes, for effective resource and minimizing response time. Then the storage management, as you know, there are so many companies that also provide storage, I would say, as a service. So to get the storage, or to get we will have an issue right here of the availability, and as we saw in distributed systems, imagine that you have a class. If you have the information of a bank account in 2 different data centers, and maybe if a data center has a shutdown, maybe you will keep the information in another data center. But what happens if the 2 data centers, I don't know, shut down? And the other one is the load balancer scalability. Here, we need to consider, imagine we're working with VMs, but VMs are inside of the nodes and nodes are inside of the data center in racks. So a load balancer needs to be intelligent enough, because the hardware industry is evolving day by day. So imagine that you have an 8-core CPU in a physical platform, and then you buy an 128 core system. So then the load balancer must be intelligent enough to say, hey, that platform is now, it was overloaded when it has an 8-core system, but now that it's the capacity increases, then you are underloaded. So I will send more tasks to you to try to get an unstable system, to try get all systems with the same amount of task or load. This includes not only CPU, includes memory, storage, and so on. And the last one is the algorithm complexity. And well, the algorithms needs to be developed in an easy way, because every time you develop a complex algorithms, you will reduce the performance and the efficiency in cloud systems. So imagine that you are making a machine learning, as we say on previous presentations. Can you hear me? I don't know. Yeah.
Yes.
I don't know why it sounds like weird. Imagine that you have give me a sec.
Yeah, we can hear you.
Well, imagine that you have virtual machines and you want to make some stress with machine learning algorithms inside of a VM. So that will be kind of hard because you need to increase to scale the virtual machine that you have, because maybe the system, if it's already with some specifications, well, in case of virtual machines, you will not have maybe the performance that you will have, and you need to scale, and that's a problem. Well, the load balancing has a model. Here you have the user request. You can have multiple user requests, and then the user request pass to the user request handler, and the handler interacts with the data center controller. But before that, before the data center controller takes the request, they check the availability of the resources. I mean, the virtual machines or physical systems that are available on the data center. And then it passes to the physical machines. And each physical machine gets the load balancer, the transfer to load balancer server, and divide the tasks by each VM. In this case, you can divide the task for n quantity of VMs. So yeah, then we have the load balancing model, classification, metrics, and policies. This is the model. The load balancing techniques are divided in two: the static load balancing and the dynamic load balancing. Basically, the static one doesn't care about the resources that they have. They don't even know that this technique don't even know about the attached systems that they have, and it's like quite easy. I will say that easy. I don't know. Easy build. So then you will have the suboptimal load balancing and the optimal balancing. Basically, in the suboptimal, I don't remember what I get nervous. Sorry. Let me check my notes. Sorry, yeah. I get a little bit nervous. Well, yeah. Basically collects the information of the resources and sends the task to the load balancer, which doesn't get the correct allocation of in the requested time, and the option. Well, this is divided into the approximate load balancing and the heuristic load balancing. The optimal. Sorry, this was the optimal, and the suboptimal was the one that doesn't determine the decision, and it calculates by suboptimal processes. And here we found some heuristic and approximations like the min-min, the min-max, and so on. I would say that. Then we have the dynamic load balancing. That is, for me, the most important one. That is the dynamic load balancing basically takes the three status, I will say, of the load balancing, like the sender initiated. That is when a system is overloaded and sends the overloaded system says, "Hey, I'm overloaded. I need help," and then he sends the tasks to an underloaded system. And then we have the receiver initiated. The receiver initiated is the other type, that when you have an underloaded system and said the underloaded system, "Hey, I'm underloaded. You can give me more tasks," and and so on. And then the symmetric, that is getting the both of these methods. And then in dynamic load balancing, we have the distributed load balancing. That is when all nodes are working for a common goal. In this case, we have two, the cooperative and the not cooperative. The cooperative is what I said, when all nodes work for one goal, but the non-cooperative is each of the nodes work in each task to achieve one goal. And the non-distributed load balancing is when you have, as I said in the example, one master node or multiple master node that sends multiple tasks to the other workers. And this is by two ways. The centralized way that I explained, one master node and multiple workers, and the semi-distributed, that is maybe multiple leaders, I will say, and those leaders send multiple tasks to the other workers. Then we have some load balancing metrics. We have the performance, the response time, throughput, scalability, fault tolerance, migration time, resource use, degree of imbalance, and mix span. The performance is based on system effectiveness. The response time is the time that takes a system to submit a request. The throughput is the amount of time that explained in the, I don't know who explained the last presentation, the amount of time that tasks get to be completed on system. The scalability is when the system accomplish the load balancing when required number of node increases, as I said, like an example of scalability, but I mean when we touch when we touch the term of elasticity, we have two, the vertical and the horizontal. In this case, maybe it could be the horizontal, but I think that a load balancer can be intelligent enough to check if the scalability can be vertical. Oh, sorry. The fault tolerance is the technique that in case of breakdown, the distributed, not the distributed system, the cluster can has the capability of balancing the technique. Like I said, what happens if one node crashes? You will need a plan B for that case. The migration time, the total time taken to transmit the request and task, the resource use, evaluated on all resources properly, the degree of instance that describes the variation between VMs, and the mix span that we saw on the previous presentation, that it represents the total time of completion taken to allocate resources to users. In this case, we can see two graphics. One is for the metrics survey techniques, and the other one is for the evaluation tools and techniques used on survey papers. We can see here that response time and resource utilizations were the two principal topics that the papers talk about. And here, the tools and techniques were mostly with CloudSIM. And then we have the poly-size. The selection poly-size is when basically identify the tasks and try to transfer the task to the node. The location determines if a node is underloaded, and if so, then it passes the task. The transfer policy makes something like that, but in this case, transfer the first checks the availability of the nodes and check the status, and then transfer the task to the VM if it's underloaded.
Creo que te muteaste.
Now we don't have
Se
your
fue la
voice,
voz.
Javier.
Yeah.
We don't have your voice.
No, still we don't have.
I don't know.
Javier, Javier. Well, we're being silenced the rest of the presentation.
Yeah, I'll phone him.
Oh, they live together.
What happened?
Chisme.
So he got disconnected or no?
No,
No,
he's
he's
still
still
there.
talking.
Okay, let me force stop him. So
Yeah.
we'll see that.
He get his
We don't have
attention.
your voice.
Sorry?
We don't hear you. Do you hear us?
I can hear you.
Can you hear us?
Hello.
Hear me?
Yeah.
Now we can.
Yeah, no.
We lost you for a second.
So
Okay.
for a
Well,
minute,
for
so
some
you can
minutes,
we can
yeah.
share again and
In what part?
so you can go one slide back.
In the policy, you just we just
One slide
read
back.
the first policy.
The transfer policy.
Yeah, the
Yeah.
transfer policy.
Yeah, I was saying that the location policy is almost it checks the underloaded nodes that well when I said nodes I refer to physical machines, but it's also with the VMs. With the VMs, check the underloaded VMs and transfer the task if the VM is doesn't have anything to do. I will say that. Then the transfer policy it checks also the underloaded VMs that we have on the system, but and it sends the task if it's underloaded. But what happens if every VM is overloaded? Then you will put the task as pending, and it will send the task until one of the VMs is available. And the last one is the information policy that it decides the time of the information collection that has the VM. We have three types: the agent, the broadcasting, and the centralized polling. And I was saying that this is the example of dynamic load balancer that we have on Intel. So I said in when you didn't hear me that I asked for permission to show you this. So well, the first step is that the load balancer, the dynamic load balancer, check the first 20 cores that we have on the CPU. If those cores are available, then you will take it. And then we divide that amount of cores in the producer cores and the worker cores. So we divide those cores in 8 and 8. And then we check the mega packet per second that we have and make the transfer between the 8 workers. And if the transfer, you can see here, worker 0 to 7, that makes 8 workers, the same amount of worker cores, and the packets are with the same amount. So you can see that the balance or the percentage to 100 is like 12.50. And if you sum all of these values, you will get 100. So that's the test that we made for testing load balancing. Obviously, this is with more complexity, but this is only to I wanted to show you this because it was very interesting for me. The conclusion, I will say that load balancing is a really needed technique on industry. As far as I know, every cloud source provider as AWS, Google, Azure, Quanta, Alibaba make these kind of techniques, and they are really important. In case of the dynamic load balancers, the paper focus on so many techniques like evolutive computing algorithms, like the ant colony algorithm, the bee honey algorithm, the PSO, the genetic algorithms to try to get an efficient way to load balance this kind of tasks in an efficient way. And there are so many. I didn't put those kind of examples in this presentation because if I do so, maybe I will take more than 4 hours because they were some more than 15 papers. So yeah, well, that's the resume of the paper as I understand. There were some trends, some needs, maybe I say to be done on terms of load balancing, because we are not efficient. Well, the data centers doesn't care about the efficiency on energy. Maybe you will say, well, maybe they will keep well, they are aware of the energy receipt that they have month by month, but they don't really care about that. Their business pays that and more. So we need to make like I will say green load balancer. So yeah, maybe. I don't know if you have questions.
Thank you, Javier. So the first question, you in your second slide, third slide, I don't know, your
this one?
No, next. No, it was more. Go ahead, go. That one. Yeah, this one.
This one? Okay.
Yeah. So what do you think? Like, I mean, basically, before we heard about task scheduling. Where does it sit here?
The task scheduling?
Do you think do you see them as the same thing, different thing?
Yeah, I think the task scheduling should be a step before the load balancer, because basically you are sending the task scheduling basically, as I understand, sends the task, but the load balancer is the one that determines if the VMs are available in term of the loading that the VMs have. So I will say that in terms of task scheduling, I will say that it should be like something like that, something like here before the load balancer.
Yeah. Anyway, that's a question for everyone. I mean, just to discuss. Okay. So who's managing the discussion? Manuel?
Yep.
Go ahead. So I don't know if there anyone has any comments on that first before Manuel starts.
I just have one question. Javier, you presented the challenges. There were no approaches or recommendations?
In this case, yes, those are the techniques. It depends on in the case that you want to apply to in this case, I would say cluster. It depends on the technique. Imagine, I don't know, if you have a cluster like me, in your enterprise, you use the way of your convenience. So the recommendations will be applied. You need to apply whatever you want depending on your necessities. I think.
Okay.
Okay, well, we can continue with the questions. So as we saw in the presentation, there are different challenges that we want to solve. So I would like to know, what do you think is the most important challenge to solve? So probably no one's remember the name of them. So I'm going to put them in the chat. So yeah.
Well, that was actually the question that I did. If the author gave any recommendation or approach for those one. And answering your question, I think each challenge is important because each one of them is pointing one specific weakness of the technology.
Yeah. Well, I do believe that one of the most important ones is the single point of failure, because if whatever is balancing fails, you are done, right? And that one, and the other one that is very important that I've seen it like in the cloud really is the heterogeneity of the nodes. It doesn't sound like that very important, but not, especially in serverless environments, you end up sometimes with very different machines, and sometimes you do have you can't predict with like a lot of certainty how things will behave. And so I don't know, I mean, I'm talking like from a balancer that is way over. I mean, I'm talking about a balancer that is over like the virtual machine abstraction. It's like an application load balancer, but I guess it follows more or less the same approach.
Well, for me, it was the single point of failure, as you said, because at that time when we got this cluster shut down by because the masternode crashed, we didn't be able to work a team of plenty engineers. So imagine in a data center with a non-distributed technique with a centralized method. So it will be hard to get up another masternode. It takes time, and time costs.
Yeah, but what do you think is more common to pass, a failure or the need of resources?
The good question.
Because in that case, if the need of resources, then the load balancer scalability
yes
should be a little bit more important than a single point of failure, right?
That's right. Yes, I think the most common one will be the geographical distributed nodes that have delay because the data centers are really, really big, and maybe, I don't know, the heterogeneous of the nodes. Imagine that you, I don't know, you buy Intel CPU, and then you wanted to scale your cluster with AMD CPUs, and you need to be able to work with both, or that's expected.
Okay, so all of them are important in different use cases, right?
Right, but some of them are more critical.
Yeah.
Okay, so well, and the next question is related with the single point of failure. So how do you think it's possible to work with the problems of a centralized solution? So one of the principal problems here is the single point of failure. So do you think there is any solution.
Any other approach
Mhm.
rather than distributed systems with Paxos or Raft? I don't know. Well, those are not distributed, but our
I mean,
approach.
I think the question goes much in the sense that, okay, if whomever is in charge of receiving the request goes down, then what? I mean, what can we do next? I mean, for example, I've seen it in code in which we have sometimes, I mean, for example, in mobile applications, we have client load balancing in which the client is aware of multiple like endpoints, so it hits them all. And in that sense, it can like overcome whenever we can overcome the single point of failure. However, it brings the burden that whomever is trying to reach the server needs to know about other available ones. So I don't know. I mean, I don't like that solution, but I've seen that one a couple of times.
I can answer my question. Into the Hadoop environment, there is an approach where if you want to obtain high availability, you can use a secondary, for saying some way, a secondary master node. So the secondary master node is going to be in sync with the master node. So if there is any problem with the principal one, you can put the second one as the principal. So that can be a solution.
Yeah, that's something like Kubernetes. Kubernetes working that way also. And the master node, one of the server is set as master, another one can be set as node, and another one can be set as like a master node. So if failure is detected in the master, then that node can be a master. Yeah, primary backup. Yeah. But the important thing here is what about the policies? I don't know if the policies are going to be stored in another part. Well, I mean, I don't have a lot of experience with load balancing, but when configuring a load balancer, you have like Javier said, the policies, how everything is going to work. But I don't know if those policies if they are inside the master or they can be accessed from another part.
Well, actually, I don't know, and that's a really good question.
Yeah, I do believe in Kubernetes, you do have a parameter store, right? That's where all those like policies should be kept. But again, if the parameter store fails, then the parameter store needs another replica and so on. I mean, the thing is that it never ends. You need like basically this be prepared and soon to be like stepped out process all the time running for every single one of your multiple.
Yeah, you need to have like a recovery plan.
Yeah,
in all cases.
Okay, perfect. So, well, the last question. So in the paper, there's a lot of different metrics that they use in the different approaches. So what do you consider to be the most important one? So let me paste all of them.
They were a lot.
Yeah.
I think Alex can tell us better because he's actually like there in the server. So what do you guys use? I mean,
I guess it depends. If you are the financial guy, I guess you are gonna be there for the cost.
Yeah.
If you are the user, maybe the response time. It depends.
Yeah, and also if you have service level agreements, right? So those are also really important.
True.
Well, yeah.
Yeah, depends from which point of view you want to see.
Yeah.
Maybe financial guys, as you say, the cost is important for me as an end user. I want fast response. For the company as a whole, maybe the throughput is very important, right? Accepting a lot of requests and processing it.
In my case, I will say the scalability, because sometimes, yeah, you have tons of physical machines in the data center, but you always need a node to do things. So you need to increase or balance the amount of tasks that you have between the nodes to don't overload the systems, because you need to keep the hardware in perfect conditions. And if you are making a lot of you are sending a lot of tasks or a lot of workloads that has a real complex I don't know, they are real complex. It's like if you were stressing the hardware in so many ways. So if you have more systems, you will be more able to distribute the load balance between each of them. So it depends on each person.
I mean, the figure that you showed at the end, it was interesting. I mean, how many researchers working on what topics? So in that figure, the response time had 23%. Basically, that shows the number of publications, like 23% of the publications are focusing on response time, 19% on resource utilization, and 17% on make spam. So it means response time is really, I mean, it's taking more attention, right? Getting more attention, and then resource utilization.
Before the class, I was discussing that with Manuel, because we disagree on that one. We know that response time is maybe the topic that has more focus between the researchers, but we agree that the theoretical things that appear on the paper are not the ones that appear on the industry. They are so different. So also Manuel and I get different responses to that question. I said scalability, and I think Manuel said that it was the other one that has the 19%. I don't remember.
Resource utilization.
Yeah, that one. And yeah, it depends on each person, and we are not experts on industry, but we know that the theory moves different from the practice.
But they are all, maybe we can say they're all equally important. I mean, if the system is not fault tolerant, it doesn't work. I mean, if the response time is so slow, the end user is not going to get attracted. If throughput is small, the company cannot handle a lot of users. So there are, I mean, if the system cannot be scalable, so I mean, they're really, I mean, equally important. But I mean, I'm not saying this is basically, of course, highlighting the importance of each topic, but I'm saying which one is attracting more attention and basically bringing more research. Maybe it's something like fault tolerant is probably is almost solved issue, you know. I mean, there are certain established way to make a system fault tolerant. So, and the cost is like, I mean, you have enough money, you can.
It's the money.
Yeah. So.
I agree on that.
Okay. Well, that's it. I don't have more questions. I don't know if there's any comment or other question. Okay.
No, so we can wrap it up. So I mean, thank you everyone for presenting. So it was good to see all these things, load balancing, task scheduling, and how basically things happen for big data all at one day. So I learned things. I hope you also in the class learning a couple of things, new things. So have a nice night and see you guys next week.
Okay. Thank you, Madi. See you.
Take care, everyone. Take care. Bye.
Thank you.
Bye.
Bye.